आई टाइम्स थीटा 2n पाई प्लस थीटा 2 ऐसा कुछ चाहिए हो। और ये हमेशा हमेशा ऐसा कोई थीटा एग्जिस्ट करता है ये बताना होगा। तो बेसिकली अगर थीटा को इधर लिखा जाए, एम रेज टू आई को इधर लिखा जाए, और तो नहीं थीटा को लेके, थीटा नहीं कॉन्स्टेंट, थीटा को लेके गए थीटा, तो हमें चाहिए कि एम रेज टू आई। हाँ तो ऐसे 2n मिल ही जाएगा ना। इन दोनों
फिर से रोटेट
सही है ना वही। तो हाँ ये
So in part 2, we were thinking that if we want to find a theta naught, for which it is never possible to divide it, the circle into as many arcs as possible, for which some arc does not contain any point. If we want to avoid that, then we need to show that for any theta 1 and any theta 2, there exists some n such that this inequality is satisfied. Because if we take z naught is e raised to I 2 pi theta, then zi has argument m raised to I times theta. So we want that m raised to I times theta has to be greater than this and less than this. So if we divide by theta on both sides, we need that this inequality to be satisfied for some I and some n. And theta 1, theta 2 and theta are fixed here.
Five minutes remaining.
तो अगर कोई
We are not able to prove it, but we think that all those z which do not lie in S, we can take any of that here. Like we think that.
2 minutes remaining.
अभी रुक जा, बेस 2 का देखते हैं। बेस 2 का भी कोई रिजल्ट होता था ना इससे?
If you look at the नहीं नहीं तो base M नहीं
30 seconds remaining.
Z no अबे ऊपर for the second one we think the initial theta should be an irrational multiple of नहीं 2 नहीं it should be an irrational number. Theta should be an irrational number. So our Z naught will be e to the power I theta, where theta is irrational, probably root 2.
Your time's up.
So in the first one, we basically have to prove that there exists a natural number t and a natural number n such that the statement is true for all I greater than n. So which is what we are trying to do here.
L is any natural number. Like
Okay, for the third one, we are trying to prove that there exists no such z0 which would satisfy neither 1 or 2.
Okay, so from the second part, we can see that, okay, from the first part, we get that 2 pi into any rational number would give us the periodic case. And if we take 2 pi into any irrational number, it would give us the second case. So there is no such Z0 that satisfies the third question.
Your time's up.
For the third part, we think it's not possible. First of all, the reason we think is, let's say we write the phase of the Z0 as a base M number, and we want to write target phases as a phase base M number. So we want to show that we can, taking powers of first Z0 phase, we can get arbitrarily close to the decimal expansion of the target phase. So basically taking powers of M in the base M represent shifting the decimal point, and so we can, if we take an irrational number, so that the numbers are randomly allotted, taking some powers of M will give us like arbitrary closed numbers towards our next phase in the decimal part. And the forward part, we can take the 2 pi factor in the front. So answer for third
Your
is
time's up.
yes. No.
Your time's up.
Okay, so for the first part, I think the set of all Z0 for which this dance will be periodic will be all the multiples of pi, all the rational multiples of pi, which is basically pi a by b. A and b are integers. And for the second part, if we take theta, which is e raised to I theta, where theta is just any real number except the rational multiples of pi, this will result in a non-periodic dance which will go on forever, and it will cover every single arc which you can form on the circle. This is because of the Kronecker delta lemma. Because also, for example, we can take z0 equal to e raised to I1, and the final equation we get, this is a natural quantity, but this is irrational, so this will never be equal.
Your time's up. I would like to ask the judges if they have any clarification for any of the teams.
Am I audible? So from IIT Delhi team, so when you deduced, like you said, Z0 is this whatever m to the power t times m minus 1's root of unity. So you started off with some t already existing. So see, we have to say how Z0 looks like which, so the t can keep changing,
Yeah,
right?
so I have written that for root of unity for all over this union over all t.
Union. So that means there are so many choices. So
Yes.
can you make a general remark like how your Z0 should be like? So that is where you didn't hit the right. Like you were very close. It's just you had to.
So do you want the expression for roots of unity? Or, I mean,
No, roots of unity is fine, but we have to see how your Z0, because that, so which root of unity, and then that is like for all t. So you want to say that your choices for Z0 is countable or uncountable? How many choices? Like, could you say something?
yeah, it would be countable. Countably infinite.
Countably infinite. So what does that, how do you deduce that?
Because for a fixed t here, we have a m raised to t.
Like, if we fix a t, then the m is the set of natural numbers which is countable, and for all t's, this will be the union of countable union of countable sets, which is.
So t is varying over what?
Okay, so t can. T तो real भी हो सकता है. T हो सकता है real.
T has to be a natural number because it is an element. K plus t is an element of a sequence. ZK plus t index. So t is a natural number here.
All right. So all right, thank you.
Judges, are there any other doubt? No. Okay. I would like to request the question making team to discuss that solution.
So basically, hello, am I audible? Hello. Okay, fine, hello, I'm audible. So basically, you have that Z0, you can write it as e to the power I 2 pi theta. And so when you do this property of m to the power I, you're multiplying m theta and then m to the power I theta. And we asked you to take the base m representation of the relevant quantity, because if I take theta in base m, what I get would be 0.a1, a2, something, something. And then when every time I multiply by m, what happens would be a1 would go here, a1 point. So m theta, it would be m a1 point, a2 point, something, something, and so on and so forth. And so for the first question, you'll end up seeing that all rational multiples of 2 pi. So whenever theta is a rational number, you have a terminating, you have a recurring or a terminating base m expansion. And so I think IIT Delhi didn't read the question properly for the first question, but like, yeah. And for the second question, what I would like to say would be, so for the second question, you have to find Z0 such that this set would be dense, right? And so to find, that is basically what the question says. And I hope everyone understands what density means, denseness means. And so we can so we have this map directly from 0, 2 pi to 0, 1. And so basically any arc here corresponds to an interval here, a, b. And for any a, b, you can find some k and l such that k by m to the power l and k plus 1 by m to the power l lies inside this a, b. And so if I find theta such that every finite combination of a1, every finite permutation of, say, the m symbols with repetition allowed is there in this theta after finitely many shifts, then I'm done. So one way you can construct this is basically you take the set of all permutations from all 1 permutations of the m symbols with repetition allowed, set of all 2 permutations with repetition allowed, so on, and then order them and then write them one after the other after the decimal point. And then for the third part, so here we see that if we miss if we don't use one of the digits, so if we have an irrational number like 0.101000100001 in base, say, 3, then it won't be dense because you won't get any number in between, say, 1 by 3 and 2 by 3, yeah. Basically, you won't be able to get every number of this form in between, and so, yeah. I hope everyone understood, and I will leave.
Okay, moving on. IIT Kanpur, you can choose your question. Okay. There are 2 cities, Sayantan Polis and Ominagar. Each city has n clubs. Denote them by S1 to Sn for clubs in Sayantan Polis and O1 to On for Ominagar. The club Si has the same name as Oi for all I equals to 1 to n. The club Si has exactly k members, each for all I. The club OI has exactly L members, each for all I. Denote the set of members of Si by Si, and similarly the set of members of OI by OI. Some eminent individuals in the country are members of these clubs subject to certain conditions. No individual is a member of 2 clubs of the same name. If you take one club in Sayantanopolis, say SE, and some club in Ominagar, say OF, then they have at least one common member when they have different names. That is, when E is not equals to F. For fixed K and L, what is the maximum value of N in terms of K and L such that this configuration exists? Note that let X be the set of members of the clubs Sj and Oj for all J. So all residents who are members of some club. Arrange the elements of X in random linear order. All the X factorial orderings are equally likely. And consider the event EI is equals to each element of Si precedes each element of OI. IIT Kanpur, do you have any doubts regarding the question? Okay, your time starts now. QC. Five minutes remaining. 2 minutes remaining.
Okay, so if we assume that, okay, we start with all the, okay, so we start with all the clubs, OI clubs, and each of them has L members, so we name the members accordingly. And since one member should be common with each, like for O1, one member should be common with all the SI clubs except for one, we'll assign any of these members to each of the clubs. Except for the first one. Similarly, we assign for all of them. So each club, each SI club will have like n-1 members at least from that assignment. And it has k members, so k should be greater than or equal to n-1. We'll do the same thing reverse to get the same inequality with, like we can assign it reverse to get the same thing with L. So from this inequality, n should be less than or equal to the maximum of k and L plus 1. Huh? We want maximum. We want maximum N, and this works for K and L, so maximum.
This works for K and L, so this should be minimum.
30 seconds remaining.
No, this side, one side
So,
also
so
works.
N should be less than L
One
plus
side
1.
also works.
One side also works.
Yeah.
Time's up.
So first, if we cannot have a member which is like common in all the groups of SIs, because then he can't be any member of OI. So like we will have at least one member who is not in each of the SI clubs, and like we can construct a matrix representing all the clubs as rows of OIs, clubs of OI as rows, and clubs of SIs as columns. And whenever, because no member is a no member is a club of SI and OI, so all the diagonal elements are 0, and the rest of the elements we can consider to be non-zero. And
so after this, we can. So if so after this, if if we so the columns of this matrix, if they are not linearly independent, then we'll lose the second condition. So
we assume that n is the max of
Time's up.
k comma L.
Time's up.
So what we will do is we will consider all the sets, all the clubs, and we will take one member from S1 and basically send that member to all the clubs except O1. So this will decrease the capacity of each of these clubs by 1. And similarly, we'll put one member here and put it in each club other than O2. So that will again decrease the capacity of all the clubs except O2. We'll do this for all n till Sn. So each of these clubs have one member now, but each of these clubs have n-1 members. But we want that this capacity should be less than the capacity there. So n should be less than L plus 1. We can do this reverse also. So this can also be L less than K plus 1. So we'll just get L less than max of L comma K
Time's up.
plus 1.
We first show that n is greater than equal to k plus L, choose k. This is because take a set S of k plus L people, P1, P2, so on up to pk plus L, and the construction is for, so like these are the number of people, for n equal to this, these are the number of people, so for the ith person, give a k size subset of this, since there are k size subsets are k plus L, choose k, you give any one subset to this I, OI, and give the rest complement to SI, SI and to complement to OI. Now SI intersection OJ cannot be 5, because if it is 5, then the k size sets of SI and SJ need to be the same. But that is not the case. So n is at least k plus L, choose k, and we think that this is optimal. Not able to prove, but.
Time's up. Judges, do you have any clarifications for any of the teams? Okay, so we would like to ask the question-making team to present the solution.
So the lower bound is correct, yeah. So basically this construction would work. And for the upper bound, you use the hint we gave in this thing. So we construct, so if for that event being true, when you pick a random linear ordering of x, it should be k plus L, it should be 1 by k plus L, choose k. Because, yeah, you can, should I go through this thing? Or it will be 1 by k plus L, choose k, you can do it yourself. And then you notice that these events EI and EJ for a different I and j will be distant. So it won't be true together, because because SI intersection OJ is not equal to 5. So maximum of SI would be greater than equal to minimum of OJ. And similarly, maximum of SJ, no, minimum of OI would be less than equal to maximum of OJ, maximum of SJ, I think, yeah. So minimum of OJ is less than equal to maximum of SI, minimum of OI is less than equal to maximum of SJ, and then we know that since both EI and EJ have to be true, minimum of SI is less than maximum of OI, and minimum of SJ is less than maximum of OJ. And using this, you will find that both can't happen together, and so the probability of union of I is equal to 1 to n EI would be summation, so it would be n by k plus L, choose k, and this has to be less than equal to 1. So you get n is less than equal to k plus L, choose k. Yeah.
IISER, which question would you like to choose? Lattice-built pyramids. All the people aliens have abducted over the years are used by the aliens as calculators. Once a person is abducted, they are dropped on an infinite integer grid with adjacent parallel grids at a distance of 1 unit from each other. The parallel vertical lines corresponding to the y direction colored with red, and parallel horizontal lines corresponding to the x direction are colored with blue. Now, the aliens are assigned to each person line y equals to lambda x, where lambda belongs to positive real numbers, with each person starting at origin on the infinite grid. Each human has to first write down BR and then walk into positive quadrant on their line. and then continue the walking sequence by writing down first B every time they come across a blue line, R every time they come across a red line. Third, BR every time they come across an intersection point. The aliens who like to use continued fractions for all the representations of the number would like to use humans and their walking sequence as continued fraction calculators by having them walk infinitely on that line. How do the aliens compute the continued fraction expansion from the walking sequence? Note that every real positive number lambda has a unique expression as a continued fraction as shown, which can be written as a1, a2 and so on, where ai is the natural number, ai can be 0. The continued fraction can dominate or may not dominate depending on the real number lambda. Do you have any doubts? If not, then the time... QMC? I'll give you 10 seconds. The time starts now. Saroj? Grid paper. Do you have grid paper? Question paper? They want question paper. Grid paper.
I think they did. It's not so easy to figure out everything. Anyway. Remind me to go.
5 minutes remaining.
So basically, when we represent this sequence, then whenever we get a terminating repeating sequence, we can conclude from it sorry, not terminating, but if we get like an RRB starting from BR, RR, BR, if this is the sequence, then we can conclude for sure that the number is rational. So the continued fraction for sure will like either repeat or terminate at some point of time. Then basically each like all these R's, the number of R's between two consecutive B's, they give the information about like they put a restriction on the values of lambda. Like if you have a grid like this, and let's say at first point you didn't reach 1, if you if you hit a R first, then that shows that lambda has to be like less than 1, like the slope is less than 1. So like if the first element after BR is R, then that reveals that the lambda is less than 1.
So now after the first BR, if we hit a R, then we know we know that lambda will be lesser than 1. So our A1 will become 0. But if we hit a blue, then our A1 must be greater than 1 at least. Now let's say we again hit a blue. That means it is above that. So again the lambda would become so A1 will be equal to okay. So now we see the sequence of blues, and from that we can after we hit the first red, we know A1. And now
so like once we hit after the consecutive sequence of B's, once we hit the second red, we know A2. And like as we keep going, if the sequence is non-periodic, then this way we can generate all the AIs from the positions of R's, from the positions of R's and the distance between two consecutive R's.
Like if we observe a repeating pattern, periodic pattern, then we can use this, and from that we can know the fraction itself, because then we'll
2 minutes
have a
remaining.
sequence of repeating.
नहीं
So let's say after this R, first if we vote first R, then we know that A1 will become 0. Then if we again hit R, then we know that lambda
Thirty seconds remaining.
तो we are above half. So again जो हमारा A2 है उसमें so now after this R, if we hit a blue, then again for the A2 we'll have we'll know A2 so repeated fraction of it will be So 2, this is the least reduced fraction. If we get a blue, but see, we count the number of blues
Your time's
and
up.
the reds in between.
Okay, if lambda belongs to integers, the sequence will just be br followed by many b's and finally again br. So we can just calculate the number of b's and add 1, we'll get the lambda. Also, if lambda is is of the type 1 upon integer, the sequence will be br followed by many r's and then a br, and so we'll get it to be number of r's plus 1. So basically our algorithm is something of this sort. We first start by finding a1, which is the number of b's before the first r. Then we invert lambda, and then we again calculate a2 by finding the number of r's between two b's. So here we can now find a2 by considering the fact that number of r's between two b's will be a2, and so on. We can keep inverting it and so on. Finally, we'll get a single equation in terms of lambda which we can calculate.
So after every time we encounter an R, if we encounter a BR immediately, that means we are switching it. That means we are taking 1 upon the value, and then again we'll count the number of B's before an R. So that will correspond our next AI. And then again when we encounter a BR, it means we are again 1 upon changing the, we are again changing this value. And then again we'll just continue like this and we'll get the entire sequence.
Your time's up.
So one observation was that for any sequence B, the number of R's behind it was equal to A0. This is the first B. And some other observations that we made were like for any sequence, let's keep a track of how many R's and B's we have covered till now. So there were capital R, R's and capital B, B's. So red or vertical or horizontal? Yeah, so the observation that we made was that when a B appears, like when the rth R appears, we
Your time's up.
Okay, firstly we are going to explain this for rational numbers. So whenever we have a rational number, as we move along the line y is equal to lambda x, at some point we will actually reach an intersection point, which means that we shall be, the human shall be writing BR after some particular point. Now until there, let's say that the human crosses writes BBs, writes capital BBs and capital RRs, then the fraction would simply be number of B's plus 1 by number of R's plus 1, because they'll have to cross that many vertical lines and horizontal lines. This will be the number of B's between the first BR and the consecutive BR.
Your time's up. I would like to ask the judges if they have any clarifications for any of the teams. I would like to request the question-making team to present the solution.
And so, yeah, basically this is more or less correct, I think. So you find out that for a given lambda, you have two observations, that R's and B's are, one of the, either R's are isolated or B's are isolated. And if like lambda is greater than 1, and another observation would be that if you switch the R's and B's, So if I have for lambda, for y is equal to lambda x, I have some sequence of r's and b's. When I switch the r's and b's, you get 1 by lambda. And then when lambda is greater than 1, you see that the number of b's between b's between r and b. So the number of, if the b's are horizontal and the r's are vertical lines, the number of b's between consecutive r's would be either floor of lambda or floor of lambda plus 1, right? And so using floor of lambda, if lambda is greater than 1, you can find a naught using this. And then from there you move on to, and then you want to find lambda minus a1. You want lambda minus a1 is equal to, a naught is equal to 1 by a1 plus 1 by a2 plus so on. And so to get lambda minus a1, what you do would be that you remove the floor of lambda, as in a1 many b's from in between consecutive r's, and then you would get lambda minus a1, and then you invert that sequence to get 1 by lambda minus a1 to a naught is equal to a1 plus 1 by a2, and so on. And then you continue this process indefinitely, as much as you can.
Yeah. IT Bombay, this is your question. Consider a species Jictophor andron in which asexual reproduction happens at discrete time steps and all organisms produce offsprings at the same instant. Let the probability of producing I offsprings by each individual in each generation be Pi for all I belonging to natural numbers union 0. Assume P1 is less than 1. These probabilities are identical for all individuals across generations but are independent of each other. Assume initially, that is at generation 0, we have only one organism. Let the number of individuals in the ith generation be Zi. The ultimate extinction probability, E, is defined as follows. Now, the not-so-evil scientist, Dr. APPU, wants to change the average value of the number of offspring produced each generation by each individual, mu, so that the ultimate extinction probability, E, is not 1. He hires your team to help him reach his goals. Give an expression of EM as a function of EM minus 1, where EI is equals to probability, ZI is equals to 0 for all I belonging to N union 0. Use part 1 to comment on mu and E to assist Dr. APPU. Note that a bounded sequence that is either monotonically increasing or decreasing is convergent. IT Bombay, do you have any questions? Your time starts now.
So sorry, I'm being. So after every generation, the people in that generation die. So after reproducing, they die. If that's not. careful.
5 minutes remaining.
So for the first part, the probability that z of m is 0 is just that the number of offsprings or the number of people in the higher generation which are still alive and all of them don't reproduce asexually. So all of them are dead, plus if all of them are already dead, in the next generation also they will be already dead. This is our recursion relation.
Okay, so the value of mu is the number of
2 minutes remaining.
the number of average offspring produced by each generation, each individual. So this will be limit of n tends to infinity of p1 plus 2p2 plus 3p3 and so on till npn, and we are taking the and we can also write mu as the number of, what is the ratio of the number of individuals in the next generation as compared to the previous generation. So this will look something like Zn upon Zn minus 1.
Thirty seconds remaining. Time's up.
So first we write the generating function of, so let G1 of Z denote after one iteration what are the probabilities of all the number of nodes present. So the G1 of Z can be given by this. And so similarly denote GK of Z. So the general expression that we get for GK of Z is let G of Z denote the same function. G is here no subscript. So G raised to K Z minus G raised to K minus 1, 0. We get this expression for GK of Z, and the probability of ZK equal to 0 is the constant term in this. So the constant term in this is basically G raised to K 0 minus G raised to K minus 1 into 0. So we already know G raised to K minus 1, 0. That is equal to EK minus 1. So EK equal to G of EK minus 1 minus EK minus 1. And G of EK minus 1 is this polynomial. So that was for part A. And
Sure. IPL.
We think that mu should be greater than 1 in order for the population to not die.
Time's up.
Okay, so for the first one, we get the expression as em minus 1 plus 1 minus em minus 1 into p naught to the power z m minus 1, because like if the previous generation has 0 offsprings, then if previous generation has 0 people, then the next generation will also have 0 people, and if the previous generation does not have 0 people, then all those people have to have 0 offsprings.
So next we are trying to comment on mu and E. So as m tends to infinity, Em will tend to Em minus 1. So we'll basically get that P naught power mu would actually have to tend to 0, which would mean that mu would have to infinity. So as it progresses, the average value as m tends to infinity will actually be infinity.
Time's up.
So basically we can define a generating function whose coefficients give the number of people that survive in the following generation, and we provide the recursive relation in these generating functions, and from this we can deduce that the P naught has to be less than 1 by E, and the recursive relation in different E's can be given through this. P naught is less.
Time's up. Judges, do you require any clarifications from any team?
Hello. From IITB, when you have written that EM is equal to 1 minus EM minus 1 P0 to the ZM minus 1 and plus EM minus 1, and I can see another equation also on the right hand side where I see expectation of Zm minus 1 in the power of P0. So which equation do you want to write? I mean, I can see two different equations.
The one that is written on the top.
That is on the?
With Zm minus 1, not expectation, just Zm minus 1.
Like I wrote the second equation just to get an estimate, like the average value for the EM, so that we can find what value should mu take to get such that E is not equal to 1 when n tends to infinity.
But anyway, first the top equation has one dispute that left hand side is deterministic but right hand side is random. That cannot never happen.
Can you repeat the question once?
No, I mean, it's not about the question, it's a remark. The remark is the top part is anyway, invalid because left-hand side is deterministic, right-hand side is random.
But left-hand side is also probability, no?
Probability is a deterministic quantity. But Zm minus is a random variable. Anyway.
So EM also depends on Zm.
No, the definition is not like that.
Now we would like to ask the question making team to.
Could you explain how you got that equation, the GKZ wala? Yeah.
Yeah, so first for, like if we see G1, it is P0 plus P1Z plus P2Z squared so on. Now, for transitioning to G2, we have to forget this P0 term because we know that in the next generation, these type of nodes are not there. So we need to, so let's assume that we have K nodes in the first generation. So that happened with probability Pk, okay? And it had a term Z raised to K with it. Now in the next, after first generation, each of the node is producing some L nodes again with this same generating function. So we need to replace Z with GZ here because there are K nodes and we need to take GZ raised to K also. So if we do like this, P1 GZ plus P2 GZ square plus so on up to Pk GZ raised to K, so on, then we would get the expression for E2. And that is not E2, like G2Z. And that is same as G1 of GZ minus G0, because G0 was this constant. So basically in any iteration, Gk of Z is actually G composed K times minus G composed K minus 1 times of 0. So that's how we got the expression.
So you call that polynomial as G of Z. Right?
Gk of Z.
The first one. Yes. G of Z.
G of Z.
And then you call that also G1 of Z.
Yeah, basically G1 because it denotes that after first generation ends.
Yeah,
what
can
are
you
the
please write down
probabilities
G2 of Z then? Can you please write down what is G2 of Z that is coming from that iteration? G sub K is defined using the relation what you have written, right?
Yes. So G2 of Z is equal to P1 times G1 G of Z plus P2 times GZ square plus so on up to. So this is basically P0 plus this term minus P0. This is G applied on G of Z. And this was G of 0.
Oh, this G to the power K is not,
it's a composition.
is a composition.
Exponentiation. G applied K times.
So what does it signify G sub to Z? Why are you computing this? What does it signify?
Yeah, so we needed to compute the constant term of this. Because the constant term of this would be the probability that Zk equal to 0, right? This is a generating function that tells me after the kth generation ends, what are the probability distributions of how many nodes are remaining. So Ek is just the constant term of Gk of Z. Gk of Z or Gk minus 1 of Z?
How do you come up with K? Because it never says that there could be only bounded number of offsprings. It could be 1 million offsprings also. I mean, what is
so k is any number. I've just written expression for general k here.
But you start with g of z.
I'm sorry. It was infinite polynomial. It's like generating function. It had infinite coefficients. It was not a finite thing.
Okay, so that is the thing you want to write.
Yeah, so constant term of this gk of z is what we need, and we know the constant term of gk minus 1 of z. So, basically we know this, and we needed the constant term of this. So we put 0 here. So we need to find g composed k times of 0 minus g composed k minus 1 times of 0, and we know gk minus 1 of 0.
Yeah, but still, for g sub 2 of z, for that, how you get, E2 or something, it is not clear. Can you please explain that? You said that g sub 2 of z is important at the second level to find out the probability. So
Okay,
you can compute g2 of z.
Yeah, so this was the expression for gk of z.
Yeah.
Let me write for gk minus 1 z2.
Already have written g2 on the right hand side. G sub 2 is already written on the right hand side. No, IITK part.
Okay.
Yeah, already written. So here for this particular example, could you please explain that why this g sub 2 z is important? I mean, you get that coefficient.
Yeah, so g sub 2 of z, if you see this, it would tell me the probability, its constant term would tell me the probability that the population has died after exactly 2 generations.
Why? It's okay. I just showed me that.
That is because that's how we had defined g2 of z. It denotes the generating function of, it denotes the probabilities of what are the number of nodes after second generation ends. So it was some q0 plus q1z plus q2z square so on up to, and we needed to find q0 here. So, and we already knew that p0 plus p1z plus so on up to infinity. So what I did was, I first assumed, let's say there were k nodes after first generation. So that happened with probability pk. Now each of these k nodes is again reproducing with the g of z1 generating function. So we can multiply pk with g of z, the whole raised to k, and sum this over all k. To get
I mean, you are not talking about general k, only for 2 if you can explain. I mean, I think you are missing one point, that when you compose g twice, g2 of z, so then you have not written that expression. It is just p0 plus p0 plus p1 times p0 times z, etc. So that expression first you need to write, right? And then only you can match the coefficients, that q0 is that thing. So argument is missing.
That's what I told, that let's assume that after first generation there were k nodes. Now each of these node reproduced with the probability distribution same as g. Okay, and now we need to find the total. Let's say n nodes were there in after generation 2. So this is basically the coefficient of z raised to l in g of z, the whole raised to k.
Okay, I think I'm done.
We would like to ask the question making team to present the solution.
So the answer we had in our head was that you take, so EM would be the probability that everything dies out by generation Z. Zm is equal to 0. And so if after Z1 we have, say, n many this thing, say we have some n many offspring, this should be equal to, then for all of them to die out, it would be e to the power m minus 1 whole to the power n, right? And so EM should be equal to P0 plus P1 of EM plus P2 of EM whole to the whole square, EM minus 1 whole square, and so on and so forth. Does that? P0 would be there, because if everything dies out by the 0th population, then everything is dead. No, EM denotes that probability of Zm is equal to 0. So, and another thing is that EM minus 1 would always be less than equal to EM. Because if everything dies out by EM minus 1, then everything dies out by EM, because there's nothing left to reproduce. And so, so we also have this, the fact that E1 is less than equal to E2 is less than equal to, so on till En. And this is all less than equal to 1. So this is a non-decreasing sequence which is bounded, so it converges to some E in E which is less than equal to 1. Now, ideally, what we want is that we use this function. So we have EM is equal to some function of EM minus 1, which is this function. And we want to use this function to find where would E would be. E would be less than equal to 1. And for this, what we would use is that f dash of, we see that f dash of x, for some x is f dash of 0, here would be what? P0 plus P1 plus 2, no, P0, f dash of 1, I am sorry. F dash of 1 would be P0 plus P2 plus 3P3 and so on. This would be the expectation value of this random variable mu. And so what we do is that, and yeah, so now we have this, and now we compare, and another thing is that we have Em is equal to f of Em minus 1, so this implies E is equal to f of E by taking the limit on both sides. And now we compare f of x is equal to y is equal to x, and y is equal to f dash of x, right? And so we see that f dash of x is both convex, as in, so these two graphs will only intersect at 2 points, at most 2 points, and then we use this, you compare f dash of y, and we also know that y of this and this intersect at x is equal to 1. Yeah, and so, no, not f dash of f of x. And so we see that y of, at f of x is equal to, f of 1 is equal to 1, and 1, and so these 2 points will intersect at x is equal to 1, and now we find out where they would intersect and so on. And so for f dash of 1 equal to 0, then they would only intersect at 1 point. And so it would only, and so E would have to be equal to 1. If f dash of 1 is less than, no, f dash of 1 is equal to 1. Less than 1, we see that it would have to intersect after this thing. But then we know that E is less than equal to 1, so E still has to be equal to 1. And if f dash of 1 is greater than 1, we would see that it would intersect like this. So, as in, it would intersect before. And so we can see that E can be less than 1 in this case. And so, hopefully that makes sense.
And with that, we have come to an end of the last deep thought session for the Mimamsa 2024. We would like to thank all the teams, the judges, the question making coordinators, the question making team, and the audience for making this event possible. Now I would like to invite the GC to conclude this session. Thank you so much.
Thank you everyone for being present here. I hope you have an enjoyable session here. I want to thank you, our judges, for being here. Now, as we are ended with the deep thought and brief thought, there will be rapid fire starting from 3:30. I request teams to be present in LHC at 2:45. Now you can move to the LHC. There is SciCon which is happening. You can move to the SciCon. After that, you guys have scheduled some interviews. You will be notified by your team coordinator. I request team coordinators to be with the team. Thank you, everyone.